So today we're going to talk about the tiny little switches that basically power our entire world, the MOSFET transistors. And more importantly, we're going to look at the absolutely incredible challenges engineers are up against as these things get smaller and smaller and smaller. It's really a constant battle against the laws of physics.
All right, let's just dive right into the deep end here. You know, we love to think of a transistor as this perfect little switch, right? It's either on or it's off, a 1 or a 0. But the thing is, when you get down to the microscopic level, reality is, well, it's a lot messier. There's this fundamental problem that engineers have been wrestling with for decades. The switch is always just a little bit leaky.
Now, this leakiness, it actually has a name. And if you can get your head around it, you're on your way to understanding the fundamental limits of all modern electronics. I mean, this is the ghost in the machine that's slowly, quietly draining your phone's battery, even when the screen is totally off. So even when a MOSFET is supposed to be off, that energy barrier keeping the electrons back, it isn't perfect. Think of it like a fence that's almost high enough. Just because of the natural heat in the system, a few really energetic electrons can still manage to hop right over it. Now that's just a tiny trickle, right? But multiply that tiny trickle by the billions of transistors in a single chip, and suddenly you've got a major power drain.
So you can see, that perfect digital model we have in our heads just doesn't quite line up with reality. And here's the most important part. This leakage isn't some bug that can be fixed. No way. It's a fundamental feature of the physics we're working with. Managing it is everything.
Okay, so if that off state is so leaky but so important, how in the world do engineers control precisely when a transistor turns on in the first place? Well, it turns out they have this remarkably precise and kind of high-energy technique to tune every single one.
This threshold voltage, it's the magic number. If you go above it, the switch flips on. Stay below it, and it's supposed to be off. And the way this is tuned is through a process called ion implantation, which is basically a way of fundamentally changing the nature of the silicon surface itself. And the level of control needed here is just, it's mind-boggling. This isn't a gentle process. It's a brute force method. You're literally firing charged atoms like tiny cannonballs into the silicon crystal to embed a super precise dose of impurities. And you have to do this perfectly to make sure billions of transistors turn on and off exactly when they're told to.
But here's the catch. As we relentlessly shrink these transistors, chasing after Moore's law, a whole new set of problems pops up. These are called short channel effects, and this is where the physics really starts to fight back. So as that little path for electricity, the channel, gets shorter and shorter, three main troublemakers show up to the party. And believe me, these are the headaches that keep chip designers up at night with every single new generation of technology.
Okay, think of it like this. The gate is supposed to be the one and only boss of the channel. But as the source and drain get closer and closer together, their own electric fields start to muscle in on the gate's territory. They help out a little too much, making it easier for current to flow. That means it takes less voltage from the gate to turn the transistor on, and the whole switch becomes unpredictable. Now this one is a really serious problem. Imagine the exit door of a stadium, that's the drain, somehow being able to lower the height of the entrance turnstile at the other end of the stadium, the source. That's the DIBL. All of a sudden, the drain's voltage starts controlling the switch, not just the gate. And that dramatically increases leakage and just wastes power.
And then there's this. This is the catastrophic failure. You have these invisible keep-out zones, engineers call them depletion regions, around the source and drain. If the channel gets too short, these zones can actually touch each other below the surface. When that happens, it creates a massive, uncontrolled current path that the gate is completely powerless to stop. It's like the floodgates have just completely broken.
But the problems don't stop with just trying to control the switch. The incredibly strong electric fields that are packed into these tiny channels create another, more sneaky phenomenon, one that affects the device over its entire lifetime.
So what in the world are hot carriers? Well, imagine electrons being accelerated to just incredible speeds inside that tiny channel. They basically become supercharged pinballs, ricocheting around with so much energy that they can actually cause physical damage to the silicon crystal itself.
Yeah, this impact creates a damaging chain reaction. One of these high-energy electrons crashes, and boom, it creates a new electron and a hole. Then that new electron can get accelerated and do the exact same thing. This creates all these unwanted currents that are a huge red flag for the device's long-term reliability.
So the bottom line here is that these hot carriers create these rogue currents where they absolutely should not be. They can leak down into the silicon base and cause all sorts of unpredictable behavior. But even worse, they can get so energetic that they physically lodge themselves into the ultra-thin insulating layer of the gate, slowly damaging it and eventually breaking the switch for good.
So, after seeing all of these different challenges, what does this all mean for the future of computing, for the devices that we rely on every single day?
You know, every new generation of smaller, faster chips you see on the market, it really represents a triumph of engineering. It's a victory in understanding and figuring out how to manage all these incredibly complex effects, from those subtle little sub-threshold leaks all the way to the long-term damage caused by hot carriers.
This constant innovation is what gives us more powerful and more efficient electronics. But it's a battle that gets harder and harder with every single nanometer we shrink. The challenges are just immense, but then again, so is the ingenuity of the engineers who are tackling them. Thanks for joining me for this explainer.